So moving on to our next part, this is actually just a revision. Okay, by right, everybody here should know everything that we are talking about here. So the first concept that we are gonna do revision is on is on concentration. Okay, so concentration, you can have mass concentration and molar concentration. So mass concentration is basically your density. Why do I say that? Because if you look at the formula here, density is equal to mass over volume. Okay, so that is the definition of mass concentration. So if I were to put a unit here, I can put here possibly kg per meter cube, or it can be gram per cm cube, or it can be pound per feet cube. Okay, all these are units for density. Okay, but one thing that you need to understand, that when we're talking about mass density or mass concentration, if you look at here, I put here rho I, right? I put here rho I, meaning that I want to find the mass concentration of component I. So you must always remember that when we are talking about mass transfer, there must be always a minimum of 2 components. When we have 2 components, only mass transfer can happen. Okay, so those are the some of the important criteria that you need to fulfill if you are doing a mass transfer process. You can have a minimum of 2, and then you can have more than 2. You can have 3, 4, 5, and 6. Okay, so for example here, let's say our system will have component A, component B, component C, and component D. Okay, so meaning that here we have 4 components. So let's say if I want to find the mass concentration or density of A, so I will write rho A is equal to MA, mass of component A over V. Now, if you see here, and if you see the formula here, rho I is equal to MI over V, and I write here rho A is equal to MA over V, meaning that here V here is the total volume of the system. This is not the volume of component A or the component I. So that's why you have to be careful. Even if you want to find the density of A, you are only using mass of A, but volume of the total system. So that is why in the general formula, I did not write I here. If I write I here, meaning that it's going to be the density or the mass concentration of component I is equal to mass of component I divided by volume of I. So this is incorrect. If you want to find the density of component I, it will always be mass of I over volume of the system, total volume. Okay, this one you have to be careful. Okay, and then if you have more than one component, you can find the total mass concentration is just that. So in our case here, we have 4 components. So if I want to find total mass concentration, is going to be mass concentration of A plus mass concentration of B plus mass concentration of C plus mass concentration of D. So this is just, you simplify and you get this. Total mass concentration is the summation of all the mass concentration of each component in the system. So this is how you generalize this equation. And then another thing, if you have mass concentration, you will also have mass fraction. Okay, so mass fraction, remember we talked about this in our IEK 101 before this, right? It's going to be the total mass fraction must always equal to 1. If you look at our system just now, how do I get my total mass concentration? Mass fraction is equal to fraction of A plus fraction of B plus fraction of C plus fraction of D. And all these things, fraction of A, B, C, and D, must always equal to 1. Okay. if I know that my fraction of A is 0.2, fraction of B is 0.3, fraction of C is 0.1. So if I ask you to find the value of fraction of D, automatically you can say that it is value of 0.4, because 0.2 plus 0.3 plus 0.1 plus 0.4 is equal to 1. So this is the meaning of this summation formula. And then if you want to find the mass fraction of each component, so for example, you want to find the mass fraction of A. Mass fraction of A is going to be equal to mass concentration of A divided by the total mass concentration of all the components. So once you get this, you can find the fraction, and if you have the fraction, you can reverse it to find the concentration of component A. So that is for mass concentration. For molar concentration, this is the symbol, right? C is the symbol for concentration. Again here, if you have for our component just now, A, B, C, D, Ca, concentration of component A is going to be equal to mole of component A divided by the total volume of the system, right? So the formula is defined as mole of I component per unit volume of the mixture. So this is the general equation. Now this one you can use either for gas or liquid, right? But then if we are using gas and we are dealing with ideal gas, right? I hope you remember what is ideal gas. So for ideal gas, we have a very special equation for ideal gas. We have PV is equal to nRT. Now this equation is only valid for ideal gas. Now by right, you should be able to change this general equation into this equation. Okay, this is just a matter of substituting and getting this equation. So how do you get this equation? Please make sure that you are able to change this equation into this equation. How do you do that? You can just use this value. Okay, try to relate this one with this one and this one, and hopefully you will get. So why is it important for us to actually know this equation? Because usually when we are dealing with gases, we are more focused on the pressure. Okay, most of the time when we are dealing with a gaseous system, we are not given usually the moles or the volume. Usually we are given the pressure of the gas, the partial pressure of component A, the partial pressure of component B, partial pressure of component C, and partial pressure of component D. By using this partial pressure, we can actually find our concentration of component A, B, C, or D. So that is why it is important for you to know how to relate this general equation of concentration with our ideal gas law in order for you to get this equation related to the concentration of the gas. So please go back and try to get this one. I've given you the hint, and hopefully you'll be able to solve it. It's very, very simple. You just need to rearrange the equation and then substitute this equation and you will get this equation. Okay, and then if you have molar concentration, you will also have mole fraction. So similar to mass fraction, the total mole fraction X must always equal to 1 and or Y must always equal to 1. So if you have XA plus XB plus XC plus XD, is going to be equal to 1. Now, if you ask me, why do we have X and Y? Is there any difference? Both of them are mole fractions. But in order for us to identify and clearly differentiate between gas and liquid, we have assigned X here is for liquid. When you see here, when you see any problems or any questions saying that X is equal to XA is equal to 0.3, XB is equal to 0.4, and xc is equal to 0.3. So automatically in your mind you can say that, okay, this is in liquid form. If I give you YA is equal to 0.1, YB is equal to 0.8, and YC is equal to 0.1, we know that this system is in gas system. So based on that, you can also already identify which system that you have. So from here, you can say that it can be, this one, it can be interaction between gas and gas. This one can be interaction between liquid and liquid. Okay, so that is just to make our life easier and to able to differentiate. And again, if you have for liquid, you can use concentration, you can use mole. For gas, you can use concentration, you can use mole, and you can also use pressure. Now this one is known as partial pressure. Partial pressure. Okay, so remember, same with concentration, same with mole, partial pressure will be, the total pressure will be equal to partial pressure of A plus partial pressure of B plus partial pressure of C plus partial pressure of D, depending on how many components you have in your system. So those are the most important concentrations that you need to use, and you'll be using it frequently in our classes.